Welcome to this tactical explainer where we're going to decode a seriously fascinating engineering challenge. Today, we're looking at how multiple input, multiple output antenna systems, MIMO for short, actually manage to operate in the highly chaotic, entirely unpredictable environment of mobile ad hoc networks. You know, whether we're talking about future 6G networks, autonomous drone swarms, or life-saving disaster relief operations. If you've ever wondered how critical communications stay online when all traditional infrastructure just completely collapses, you're in the exact right place. So let's quickly pull up our mission overview for today. We'll be hitting 6 key areas: the MANET Battlefield, the MIMO arsenal, the core detection problem, linear and nonlinear tactics, advanced precision strikes, and then we'll wrap it all up with a mission debrief. All right, diving into Section 1, the MANET Battlefield. To actually solve this problem, we first have to fully understand the volatile environment we're dealing with. Picture a disaster response scenario, or a tactical military deployment, or even a massive swarm of autonomous IoT devices. In these situations, you don't have the luxury of fixed cell towers or base stations. Enter the Mobile Ad Hoc Network, or MANET. It's a completely decentralized, self-organizing wireless network. And what makes this so incredibly unique is that every single moving node, whether that's a drone, a soldier's radio, a vehicle, acts as both the endpoint receiving the data and the router forwarding it along to everyone else. The network literally has to configure and heal itself on the fly, as all those nodes are physically moving around. And this illustrates perfectly why these radios operate in some of the most demanding conditions imaginable. Because everyone is constantly in motion, the network topology is shifting second by second. You have absolutely zero centralized coordination to manage your resources. Plus, the signals themselves are bouncing off the terrain, causing severe multipath fading and interference. The very movement of the nodes is actually triggering Doppler shifts that distort the frequencies. And to top it all off, these are portable devices, right? So they are severely constrained by limited battery power and really narrow bandwidths. Which leads us to the ultimate question of survival and efficiency out in the field. How exactly do we push high volumes of data through all this chaos without simply draining our batteries in 5 minutes, or eating up bandwidth we just don't have? Well, to answer that, we turn to our primary technological countermeasure. Section 2, the MIMO arsenal, our heavy artillery for data. Multiple input, multiple output, or MIMO, is essentially a massive force multiplier. Instead of relying on a single antenna, MIMO deploys multiple antennas at both the transmitter and the receiver. By doing this, it exploits what we call spatial diversity, which is really just a fancy way of saying it uses the multiple bouncing paths of the wireless signal to combat that fading we talked about. It also uses spatial multiplexing to send totally separate data streams simultaneously over the exact same frequency. So suddenly, without using a single drop of extra bandwidth or transmit power, you've instantly increased your throughput and your ability to support highly dense, traffic-heavy networks. Now check out our core telemetry equation here. This simple formula represents the entire wireless transaction. Y is our received signal vector, what actually hits the antennas. H is the channel matrix, representing those invisible, highly dynamic wireless paths between the antennas. X is our original transmitted signal, the pristine data we actually want. And N is the unavoidable background noise. The entire game of MIMO detection is hidden right here in this one piece of math. So we've got the hardware in place, but now we have to calibrate the software to actually decode it. That brings us to Section 3, the core detection problem. The primary conflict here, what we call the receiver's dilemma, is unscrambling those transmitted symbols, our X, from the noisy, distorted signal Y. To do this, the receiver has to constantly estimate X by relying on that channel matrix, H. But remember, H is changing wildly because the nodes are moving. So we're faced with this truly agonizing trade-off between detection accuracy and computational complexity. If you want perfectly accurate data, you need intense processing power, but we're on portable, battery-powered radios. And this computational complexity doesn't just grow linearly, it scales up aggressively the more antennas you add or the higher your data rate gets. Let's look at how we actually fight this battle. Section 4 covers the basic algorithms, linear and nonlinear tactics. First up, we have our linear detection strategies. The most basic is zero forcing. Honestly, think of zero forcing as a blunt instrument. It simply inverts the channel matrix mathematically to cancel out interference. It's incredibly fast, uses very low computing power, but it has a fatal flaw in a MANET. It severely amplifies background noise. If your connection is weak, zero forcing basically just turns up the volume on the static. Next is MMSE, or minimum mean square error. This is a slightly smarter, more balanced approach. It factors the actual noise variance right into the formula, balancing out the interference and the noise. It performs way better in chaotic conditions, but because it's still just a linear mathematical trick, it hits a hard wall when we try to push really high data rates through it. So let's see what happens when we introduce nonlinear tactics. A really popular method is successive interference cancellation, specifically architectures like VBlast. This operates totally differently. It acts essentially like peeling an onion. Step 1. It actively seeks out and detects the absolute strongest, clearest data stream in the mix. Step 2. It subtracts that strong signal's mathematical footprint entirely from the received signal. Then Step 3. It repeats the process for the next strongest signal, and so on. By stripping away the loud signals, the quieter, hidden data is gradually uncovered. But here's the catch. This step-by-step peeling carries a severe tactical risk called error propagation. If the algorithm misidentifies that very first supposedly strong signal, it's going to subtract the wrong math from the whole equation. Every single subsequent calculation for the weaker streams will be irreversibly corrupted. It's a complete domino effect of bad data. So linear is sometimes too blunt, and basic nonlinear has cascading risks. Let's step it up to Section 5, Advanced Precision Strikes, looking at optimal and emerging systems. When we talk about absolute perfection in decoding, we're talking about maximum likelihood detection. This is the theoretical gold standard. This algorithm brute forces the problem by searching through every single possible combination of transmitted symbols and picking the one that best matches what was received. It gives you theoretically optimal accuracy with the lowest possible error rate. The catch? Because it searches every combination, the processing demand grows exponentially. It requires impossibly high computational complexity. For a soldier in the field running a real-time, low-latency MANET radio on a battery pack, doing billions of calculations a second is just a non-starter. Which brings us to a brilliantly elegant solution, sphere decoding. Sphere decoding is a highly practical compromise. Instead of searching the entire infinite universe of possible symbols like maximum likelihood does, it draws a bounded region, a mathematical sphere, around the received signal. It only searches the highly probable candidates inside that specific sphere. This restricted search gets you near optimal, almost perfect accuracy, but at a significantly reduced computational cost that a portable processor can actually handle. And now we're seeing the incredible dawn of next-generation deep learning models stepping into the arena. Instead of hard-coding the math, engineers are deploying neural networks that learn the complex, messy statistics of the wireless channel directly from raw data. What makes this a total game-changer for mobile networks is that it shifts all that heavy, battery-killing computation offline to the training phase. Once it's actually deployed on the battlefield, the radio is just executing inference, which is lightning-fast and highly adaptable to those wildly fluctuating, time-varying mobile channels. Okay, it's time to consolidate all our intel and review how these systems stack up. Section 6, Mission Debrief. Now, before we look at the final comparison, we absolutely must ground ourselves in the unique constraints of the MANET environment. Remember, these are not your living room Wi-Fi routers. These radios are constrained by rapidly changing channel conditions because of extreme node mobility. They have strict processing and power budgets, and an absolute, non-negotiable necessity for zero-lag, ultra-low latency detection. And they have to pull this off while constantly struggling with delayed or just downright imperfect information about the channel itself. So, the crucial takeaway is summarized perfectly right here in our performance matrix. Zero forcing and MMSE offer great simplicity, but they just don't have the accuracy for complex ops. Maximum likelihood is way too power-hungry to be practical. Successive interference cancellation offers a decent middle ground, but look at those bottom two rows. Sphere decoding currently strikes the absolute best balance for active deployments today, giving you near optimal accuracy with manageable complexity. Meanwhile, deep learning is fast emerging as the ultimate, highly promising, low-latency solution of tomorrow. As we look toward future directives, things like ultra-energy efficient hardware and adaptive hybrid detectors that switch algorithms on the fly, I want to leave you with an incredibly fascinating thought. As these deep learning networks continue to evolve and become deeply integrated into mobile ad hoc networks, we have to ask ourselves, are we approaching a point where our tactical radios become so advanced they can actually predict chaotic channel interference before the physical signals even arrive at the antenna? It completely redefines the limits of wireless communication. Thanks for diving into this explainer with me. Keep questioning and keep learning.